This session is about Nuagenetworks. So we are in the SDN arena, so software-defined networks. So my name is Wim Hendickx. I'm running the European consulting team. So I'm based in Europe, based in Belgium, so close by. But I think I have to do this presentation in English rather than Dutch, right? So, yeah, first of all, yeah, this doesn't work, of course. I'll start with a bit of an introduction, right? So who is Nuagenetworks? I don't know who in the room doesn't know about Nuagenetworks or has not heard about it. Okay, one person, the rest is fine. So that's good. So we are actually a part of Nokia these days. So we started in Alcatel-Lucent, so we are actually part of Nokia itself. And in that we have our own brand, so we are kind of like an own venture within the whole group, right? So we are based in California headquartered. There is also some development in Europe, actually in Belgium. So there is a small team, today about 10, 15 people, but it's growing there as well. And so what we do actually is we are actually using a number of open source tools to actually try to solve what we call the software-defined networking stack, is actually, or the networking problem, is try to make networking simple. That's basically our mission in life, okay? I don't know whether that's a good or a bad thing, but what you see these days is that networking is being consumed by multiple different ways and people. And if you look today, we are mainly going to talk about OpenStack, but what you see out there is there's a number of other tools evolving in the same remit, mainly in the Docker and the container workspace, and as such, you have the similar set of problems as we have in the cloud environment. Now, so as I said, is what you typically saw is when we started with virtualization, I think compute and storage was actually very well defined and very well, let's say, virtualized or cloudified. If you look to the networking, it's actually a bit of a different problem because we can say, okay, we can virtualize VLANs, but typically a networking problem is bigger than just a compute node on which your workloads runs, right? And we talk about networking, about instantiating services, which are either layer 2, layer 3. We talk about security services, not firewalls, and typically not in one location, but across multiple locations, and so on and so forth. You need to connect it to either the public internet for consumption or to the enterprise branch, and all of that is what we call, or the networking problem we are trying to solve with an SDN play, right? And so this is where we started, and we started, so our first release of the product was actually in 2013, right? And if you look initially, what was our mission in life is actually explaining to people what SDN was all about, right? And so if you look on, let's say, the summary of it is like, it was complex, it was costly, it was customized. So what we see today in a lot of deployments of networking is that you have still quite a lot of manual operation which happen on different workloads, right? And which is either a firewall, is a router, is a switch, and typically you have to connect it then also to an MPLS network sometimes. So, and all of these things are, let's say, not so well, let's say, abstracted or consumable. And what we are doing actually with SDN is we make it what I call consumable and abstracted in a way that for people who don't know the details, because our users are typically the applications which run somewhere, right? Either in a public cloud or a private cloud or at a branch or whatever. And those applications typically have no clue what is going on underneath. What they just care about is give me connectivity. And what the networking people care about is making it work that it actually is reliable, and making it work such that it's secure, right? And that's basically our mission statement where we come about from an SDN framework, right? Now, in order to solve that problem, it's actually a very hard, because actually if you look at networking starting at the branch, on the, let's say from the enterprise, in different compute nodes on a data center side, and then consuming that across different locations, right? It's a difficult problem to solve, right? So what did we say when we started SDN, and this is where overlays came from, is like we said, okay, we need to make that problem statement a bit, let's say, easier to resolve, and as such what we said is we control endpoints, right? And the connectivity between those endpoints would be based on IP networks. And why did we select IP? Because it was ubiquitous. So you can connect typically any workload from anywhere across the world through the internet. Let's say it, right? Just to make it simple. And as such, what we said is, okay, let's go and drive our, let's say, the middle bubble towards an IP-based environment, because we can transport, if we can transport a packet through an IP-based environment, we can actually make it a solvable problem, right? Because if we are going to try and program every single hop along the way, it's going to be very difficult, because if you look within a data center, that's probably resolvable, but if you want to go across, and if you have, let's say, sometimes people have private data center interconnect, that's still solvable probably, but then if you go to the MPLS environment, or if you go to enterprises which are connected through mobile networks, or through XDSL or whatsoever, it becomes a very difficult problem, right? And as such, this is where overlays came from, is that we said, okay, let's make it the connectivity, or let's assume that there is connectivity between the different endpoints. And that connectivity was IP. And then we came with a protocol, or with a, let's say, a protocol which is actually VXLAN, and we said, okay, we need to be able to transport layer 2 or layer 3 across that IP-based fabric, and that's where VXLAN came from, right? And as such, what we then have is we create overlay tunnels between endpoints. And in this case, this would be, let's say, virtual machine. So let's say compute nodes which are running virtual workloads. But those could very well be containers. But this can also be a connection towards, for example, bare metal, a database server, which is typically a physical entity. And that could be then instantiated on a physical switch, right? Or this can be instantiated on an enterprise CPE, which is actually running the same set of toolkit and the same set of programmability, but could also be, for example, a public cloud. So like having an endpoint in an Amazon or in an Azure cloud or in a Google cloud environment, you could also program that type of entity, right? And so as such, what we do is we program endpoints and we create tunnels across them, right? And in some cases, we even put security underneath with IPsec, because they are in an untrustable environment and you don't want people to see or look inside what is actually running, because if you put a workload, for example, in an Amazon or in an Azure, you actually you would like to have encryption, because you don't want people to see what you actually transport across an untrusted environment, right? So when we allow that flexibility to be created, but by doing so, we make it, let's say, I would say, a resolvable problem on how to fix a networking. And what we do is we program endpoints which are connected to that fabric, which we call, okay? Now, what did we do and how did we solve that? Is we created a product which is the VSP, which is the Nuage Virtualized Services Platform. So that's the overall system umbrella. And what we do is we created a VSD, which is actually our policy engine, which is holding those network constructions. And I'll come back to what those are. We have then a controller which is actually able to scale out, right? Because if you say, if I have one data center, that's fine, you can probably do that with a single controller. If you have multiple, do you want that same controller to control the other data center? If you want that same controller to control your branches and so on and so forth, you want to have what I call a Lego block system, which is actually able to scale out and be putting those systems into a controllable or uncontrollable environment, depending on where your endpoints are residing. So we are able to federate those controllers, and we use BGP between them to actually make this networking construction visible across different controllers where your endpoints are connected to. And then we created something, so we have our data plane, which is basically the and we have two different types. One is more a data center oriented workload, and another one is more what we call for the branch, what we call SD1. I don't know whether people are familiar with software-defined WAN and software-defined data set. Software-defined WAN is today what you typically see when you connect an enterprise. You connect them via traditional, in a lot of cases it's MPLS VPNs, right? And you connect them and you connect it via an Ethernet or a DSL line or mobile, right? Or an LTE dongle. But what we see right now is that rather than doing a traditional connection with a VLAN configuration towards the MPLS VPN network, what people do is they build hybrid ones, so they connect the CPE to both internet and MPLS-based environment, and they control with the same principle as the software-defined data center that endpoint as well. So what you can do now is what you see, or where is this, let's say, interesting for, is that typically internet these days have higher speeds and have, let's say, less cost compared to an MPLS. So what a lot of enterprises are going for is actually they are trying to connect the CPE to both an internet connection or an MPLS VPN. And as such, what the SD-WAN does is actually they select the best path depending on SLAs and application-based statistics, right? And so as such, you use the same philosophy as which we have in the software-defined data center, but the difference there is that from an installation point of view, the data center side typically gets installed based on the installation tool you saw before, a session on HP Helion. So you have your Ansible tools kit or whatever to actually do the installation of all the different services which are running on your compute node, and the VRS would be part of that installation. If you go to the branch and the enterprise side, you come in an untrusted environment, right? And you want to make that installation very simple because you actually want to have it run as kind of a retail use case where you buy a DSL modem or a cable modem from X, Y, and Z, and you basically are able to install that as a retail device, right? And as such, what we do here different compared to that is that we make that bootstrapping process or that activation process very simple. And so we use the same tools as what you have today on your Apple phone and things like that. We have two-factor authentication, so we can bootstrap it, then send an SMS, and you activate it like that to make sure that the trusted entity is actually installing it, right? But from a conceptual point of view, it is the same controller and the same network database which is actually programming either the left side or the right side. And where this is nice from, if you go to an enterprise today, you can actually connect or control the networking from the location at the enterprise side all the way up to the cloud. And if the cloud is public, for example, AWS, or if the cloud is private, we don't care. It's one solution which is able to control all of these endpoints, okay? So now, before we go into a bit more detail, is that what is a network construction, right? Is that we can say it's a VLAN, right? But it's much more. It's a routing entity, it's your IP addressing, it's connectivity towards the WAN, it's sometimes service chaining, because sometimes you want certain workloads to go to a particular firewall, or you want to have certain load balancer into the chain. You sometimes have NFV workloads which needs SRIOV, right? And you have different types of, let's say, networking policies which need to be instantiated depending on your workload, right? Now what we did is we built them with templates. Why? Because you are able to reuse them, right? And such that it's easy to consume. That means that your network design people, they design those templates, and then your operational people, they just use it. We make it also as such that if you have security people who says, okay, I have a certain vulnerability and I want to stop this workflow, that they have independent control over the network policies from the real network construction and stuff like that to make it consumable and stuff like that, because that's very important from an operational point of view. But what I try to say with this slide is that networking is much more than programming a VLAN on a compute node. It's actually building that policy which is able to control all the different endpoints based on a very, let's say, abstracted language which is easy to consume. Because here people have no clue whether they use VXLAN or whatsoever. It just all happens for them. Now, as I said, so if you look on how the system then works, is that you have the VSD, VSC, and then the different VRSs. How do we work with an OpenStack? Is we plug the API onto the VSD, onto the OpenStack controller node, right? So there is, and we have different levels of plugins. So we have an ML2 plugin, which we typically use for SRIOV, ISO NFV-based workloads. Or we have a core plugin, which is able to go straight into the system as well. So you can pick and choose depending on your deployment scenario. You can actually, besides OpenStack, also run VMware. We have an integration in VMware. You can run, besides that cloud stack, you can run a Kubernetes environment, you can run a Mesos environment, you can run Docker Swarm. It's the same API, and they can all run simultaneously. And it can be multiple OpenStack instances or multiple VMware instances, and so on and so forth. Right? So it doesn't have to be limited to a single one. Right? Now, as I said before, how does the system work? If you need, let's say, 2 data centers, you have the same VSD, and you have a different VSC pair. And you have the VRSs, which are running your data plane onto the different servers. So it scales out. If you have a third, you could have another pair here. Or if this is a public cloud, it would be their own system. Right? Because we see in a lot of our deployments, most of the data center, at least you have 2 for let's say, high availability reasons. And in a lot of cases, we have more than 2 even. Now, the other thing what is important these days is that it's not only for VMs, but it can also work for containers, right? So for us, whether you run Docker, Linux containers, or LXD or so on, it doesn't really matter, right? And then, as I said before, connecting the branch to it, it's using the same controller pair and actually running the NSG type of software either as a physical device, as an x86, or as a VM at the customer premises, and we build the network construction as a whole. And so all of that is defined as a single template within the VSD, and it's then from the moment that entity is instantiated, you actually program the networking policies onto the respective endpoints which are part of that service, and traffic gets instantiated. Okay? Now, why do we exist in an OpenStack environment, right? So we are in an OpenStack meetup, so we better talk about that, right? So a simple way I always explain it is the following. If you look to standard OpenStack, and we have Neutron, right? So Neutron is basically where we plug in. As I said before, we either do it via ML2 or via the core plugin. But if you look under the hood, what is happening is that if you look into a compute node and you would look at the Linux bridges and interfaces which get created on such a system, you're actually, and I think the slide is not so good, but you will get the slides distributed anyhow, but you see that the complexity of what's actually running on the compute node of an OpenStack, it's pretty complex, right? So if you want to debug or find a problem, so for us to explain why do we exist, we make things simple. Because for us, we create a single bridge and we attach either a VM or a container to it, and that's it. And all the tunneling, and whether you use layer 2 or layer 3, or whether you run NAT to underlay or SNAT or PAT and things like that, it's all happening here. And what do we use? We use Open vSwitch. So it's running within the kernel. If you take a Linux distribution of HP or of Red Hat or of Canonical or whatsoever, it's part of the kernel typically, so which is installed. So you don't have to rip out the kernel, you just use what is there. What we do is we change the user space of the Open vSwitch to actually be able to do the smarts which I actually talked about. And that's why we call it a VRS rather than an Open vSwitch. But in essence, it's OVS with a replaced user space agent. Now, what does that mean? This is another way on how OpenStack works, so a bit more detail. So this is what we do. You get full distribution. So for example, if you have in a traditional OpenStack deployment, you have a compute node and you have a network node, right? And a network node used to be a single point of failure. In the meantime, they have built high availability in there and things like that. But for us, you don't really need a network node at all because everything is running in a fully distributed manner. So that means if you send a packet, whether it's routed or switched from host 1 to host 2, you never go to a centralized entity which is routing the packet from A to B. If you want to do NAT, which is one-to-one NAT or PAT to the underlay, or if you want to go straight to the underlay, or if you want to run SRIOV, you actually do that locally inside of the node which is instantiating the service. So you never have any choke point into the network with respect to those network construction. Right? And that is important capability because you actually optimize the total cost of ownership by always sending the traffic to the most to the right endpoint using a straight connection from A to B. Now, what is always interesting, and that's one of the discussion, is that if you use overlay networks like VXLAN, you have to go out. You have to break out, right? Is that because you can live in your own isolated environment, and if everything is Nuage, life's good. But that's typically not the case, right? So we typically have to talk to what we call the traditional environment. As such, we work with different type of use cases. So first of all, we can go straight out. So from the node, we can actually go straight to the underlay. And that can be done using either one-to-one NAT or PAT, but also going direct out, and then you actually have to, let's say, advertise your host route into the underlay, right? So from a scalability point of view, that is not always good, but some people like that. So for example, if you look to container type of environments where they use VXLAN under the hood, you actually avoid double overlays and stuff like that with that. Okay, but I'm not going to dwell into that. But besides that, we also have software gateways and we have hardware gateways. So we work, for example, with Dell people here. So we work with Dell switches, so we can program Dell switches. We can program Arista switches. We can program Cisco switches and so on. So we have our own hardware as well. So we try to give you the flexibility depending on the environment you're in. And we program different underlay switches depending on the choice of the operator itself, such that you have the ability to break out towards your dedicated environment. We are not limited only to data centers, let's say, based hardware. We sometimes also have to program MPLS-based routers, like we have our own, let's say, 7750 family, but you have MX routers or ASR 9Ks, and typically also those we have connectivity with, and we provide interworking to actually be able to break out to the, let's say, traditional MPLS environment. Okay? That's typically a huge point of discussion in every conversation which we have, right? The second thing what we do is, given that we have this federated control plane with BGP, we avoid a big choke point which you have in Neutron, right? So Neutron is actually, if you look to big deployments which are going beyond 200 servers, you actually typically start deploying different cells, and you have to split up the environment, and you start to have different Neutron servers and things like that. So we avoid all of that because what we do is we actually have a single API towards the Neutron database. So actually here the Neutron server connects to the VSD, and then all the distribution of all the routing happens through our controller, right? So you don't have, you go any longer via the RabbitMQ bus or whatever MQ interface towards all the different compute nodes or the network nodes. You actually have a single API call to the Neutron server, and as such what we have seen in a lot of deployments, which are rather big, that we actually offload a bunch of complexity and choke points onto that system by actually having that API interface rather than using the traditional environment. Now, besides that, we offer also quite a bit of value add on top of the Neutron capabilities as a whole, right? So if you look at the templating which is there, we offer, for example, multicast services, right? So given that we are typically coming from a telco type of environment, there is always multicast type of environments available. Even in enterprises, we have multicast services. So we offer multicast capabilities in that stack. Same is true for, if you look to the actions in the policy definition of an OpenStack, you can say, forward or something like that. We can do drop, we can do redirect, we can do mirror, we can do stateful firewall, start logging, and things like that. So you get a whole bunch of extra value proposition in terms of, let's say, security auditing. So people want to know which flows are running into my network. Give me visibility of the different construction, and we just are launching a new product which we call Security Insights, where we actually, given that we know the network construction on how those workloads work, and given that we know the flows which are actually running into there, we can actually help you in trying to spot and identify security vulnerabilities, because we can actually correlate the flows to the firewall policies which are actually configured in that environment. And by doing so, we are able to offload and actually help into the security analytics, which is one of the big problems which we have. But as you see, the amount of capabilities which we offer on top of the standard Neutron stack is actually much bigger, and that's another reason why a lot of people take an SDN versus using a traditional neutron type of stack. Now, as I said before, the world is not only VMs any longer, right? If you look today, in all of our conversations which we have with our customer, not in all, but 80 to 90%, we have conversations around this. And this is for DevOps type of use cases. So it's not only anymore about OpenStack, but it's also a lot about OpenShift, right? It's also typically a lot about Kubernetes. They have a mesos environment. In a lot of cases, it's also connecting not only the private clouds, but connecting to public. And we also recently launched what we call a VRSB, is to be able to instantiate the networking on a bare metal without actually running a virtualization layer onto the stack, to actually be able to run the software-based OVS directly into the Linux system without actually running any virtualization. And that is to be able to offer, for example, a lot of people have a HANA-based system, which is running on Linux, and they want to actually have the same network policies which we define for virtual workloads also available into that system, right? So as such, what you see is that it's not only VMs, but it's actually a whole bunch of entities which you want to control, okay? On top, we provide an open system because a lot of people, they say, okay, give me this and give me that and give me that. There is a number of our customers which develop some of those plugins by themselves, right? So we are able to give you, for example, so we have integration with F5, AVI, Fortinet, Palo Alto, so all the big appliance vendors, because they typically are there and we have to interwork with them. So a number of them, they created their own plugin for X as a service. We have then all the different cloud infrastructure environments for which we develop a number of tools, but there is some of those plugins which some of our customers have developed. Cloud hybrid interconnects, you could develop by yourself, because we provide you the APIs to do so, as well as the data plane side. So we give you, at Nuage, we see it as a platform on which you have these open interfaces and you can actually able to provide plugins for the respective units which you would like to control or have support for. And we do some of them ourselves, but you allow to develop some of these things ourselves. If you see, we are in all of the distributions, right? Given our track record, so we have like close to 100 deployments these days. We are actually we have deployments with all the different stacks, right? And so with HP, so DCN, which is the HP product, is actually part of the Helion stack, okay? But we support from Havana to Mitaka, and we are very close. So for example, when Newton comes out, we actually within 3 to 4 weeks, we actually have support for that release within Nuage. So we are actually very close in contact with actually the OpenStack release cycle, so that we actually are able to give the latest and greatest as quickly as possible towards our customers, right? So in a nutshell, what does Nuage brings on top of a traditional OpenStack type of capability is that first of all, I think we extend the networking constructs which are in traditional Neutron. We allow you to give many more options, right? The second thing is actually the operation side of things. So if it comes down to this programmability, because a lot of people who come from a traditional network background, they are used to a CLI and they configure this box and they have full control. So the problem which you have these days is, okay, now magic happens, right? But what if something goes wrong? What do we do? How do we troubleshoot and things like that? So we have some tools which is called the VSAP, which is the assurance platform, which is able to help, for example, correlate the underlay to the overlay, because we assume it's one big fabric, but something goes wrong. So we have to provide you the visibility of that. So we provide that. We have mirroring, so we have a lot of operational side of things. And then we give you the ability to not only have your private cloud connected, but connect also the branch as well as the public cloud and be able to have multiple workloads going from virtual machines to containers to bare metal. And I think that's basically where we bring added value on top of a traditional or a simple OpenStack Neutron environment. And with that, I would like to thank you. And if there is any questions, I'm happy to answer them. Yes?
So you mentioned that you have the capability to program switches of various brands.
Yes.
So how does that work? Is that a plug-in model, or is that do you make those things, or is that the vendors that have to supply some piece of code to you?
So the nice thing, what has happened in the industry, and now I'm talking mainly about the, let's say, the traditional data center switching vendors. Right? So for example, to Dell or to an Arista and stuff like that, what we have developed across the industry is a schema which all of us support. And so it's called OVSDB is the protocol. And so we use OVSDB schema for that. And so we have support in Nuage for layer 2, for layer 3. So we can do routed VXLAN. We can program ACLs, QoS.
As long as the switch vendor makes sure they support the protocol and you...
Yes, and what we typically do is we want to validate, we typically validate it to make sure that it's supported, right? But that's basically it. Now, what you see from the OVSDB schema is that, like Arista has a CVX, so we work via the CVX with Arista, for example, whereas towards Dell Cumulus, we go straight to the switch. So it depends, so then the support model to the vendor depends a bit, but so you typically have two models, but that's how it works. But the good thing is that we have a common data model, which we all behind, and that's what we use. So as such, we have done, and actually we didn't make a lot of noise about that, whereas today, if you go to IETF and stuff like that, it's all about Yang, netconf Yang and stuff like that, and it takes ages before a data model is defined. If you look to the OVSDB schema, it's on the internet, it's on GitHub, people have used it, there has been some comments, but it's there, and it was developed in less than a year to 1 year to 1 year and a half. Okay? All right. Thank you.